Okay, let's do the last presentation, okay? You know, I like everybody to pay attention to the presentation. I think this is very important learning process for this course. Okay, do the presentation and listen to the presentation and study. Pay attention to the class. It's the very basic or is important, essential attitude for this course, okay? Okay. So, Nan. Okay, the last one.
Okay, so everyone, today I am going to present the assignment to I have gathered the height and weight data of male and female students in grade 9 of Thailand. This is the weight in kilogram, and we calculate from kilogram to pounds, and this is the result. And the height, we have the height in centimeter, and I have calculated to inch, and this is for above 5 feet data. And for gender, I enter 1 to represent male and 0 to represent female. Okay, after we estimate from the e-views program, the results show the relationship between the independent variable and dependent variable of the two measurement units was positive correlation, but with different coefficient. So for kilogram per centimeter, if height increase 1 centimeter, the weight will increase 1.1x to kilogram. For pounds per inches, the height increase 1 inch, the weight will increase 6.6 to t pound. Furthermore, it was found that the but it's we found that the R square was okay. For the coefficient, for the kilogram per centimeter, if height increase 1 centimeter, the weight will increase 1.1 to 1x to kilograms. For pound per inches, if height increase 1 inches, the weight will increase 6.6 to 3 pounds.
Okay.
Furthermore, it was found the R square we found R square was 22% and the adjusted R square was 0.2 for both measurement units.
Okay. Okay, usually if you just look at R square and just the R square, just the R square always smaller than R square. Okay? All right.
Yes. Yeah, if you see in the graphs, you can see the R square and adjusted R square was same for the both measurement unit.
Yeah, okay.
Yeah. And step 2, after implementing by e-view for kilogram per centimeter, units was for the maximum weight is 94 kilogram and minimum weight is 38 kilogram and maximum height is 177 centimeter, and minimum height is 155 centimeter. For pounds per inches unit was found the maximum weight is 207.23 pounds and maximum weight is 87.77 pounds, and the maximum height is 69.68 inches and minimum weight is 61.02 inches. Okay. For the step T, the result, we found the beta zero is constant in the kilograms per centimeter is 60.86 and coefficient of height or beta 1 is 1.1x2, and for power per inch units, the constant of beta 0 is 96.34 and beta 1 coefficient of height is 6.62. And step 4, we found the beta 0 and beta 1 of the kilogram per centimeter and pound per inches same the equation of 2.6. And the step 5 for intercept adjust R square, we found the process of measurement units in kilogram per centimeter and pound per inches. After estimating by eViews program are 0.2.5 with a single independent variable same, and the adjust R square is used to compare the explanatory power of the model equation with different independent variable. Usually, if an independent variable is added to the model equation, the R square always increase or not change. This does not mean that any independent variable or added can predict dependent variable and may cause overfitting the model, resulting in a less effective predictive model. But adjust R square will help determine the usefulness of variable. If an independent variable is added to the model equation and adjust R square was increased, then the independent variable can predict the dependent variable. But if the adjust R square was decreased, the independent variable can be predict the dependent variable. And step 6. After we added gender or males, we represent male for in the gender and independent. That is the independent dummy variable to the equation. From the gender variable is a dummy variable. We enter once for represent a male student. The coefficient of gender is measurement units in kilogram per centimeter is minus 0.0065 So the weight of the male less than the female 0.0065 kilogram is equal. That is equal to 0.0143x2 pound in pound per inch. After you calculate this from kilogram to pounds.
I think this is the first case we see with the gender as a variable, the coefficient is negative, right? We haven't seen any others project with gender is negative. So, this really says something about it, okay? So just look at the coefficient. Just look at the coefficient. You will not know the importance of this variable. Even the sign, according to the theory, and so far, for all of your projects, okay, in terms of adjusted R square, there's no much difference with gender as another variable, right? There's no difference. Means what? Means gender is not matters for the person's weight. Okay, but we will see all the important stories later on. Okay, but since this one, when we do the hypothesize expected signs for the gender, usually we'll see the positive relationship. I think, male is taller than a female, generally speaking. But does that make difference? We don't know. Actually, we don't know because we see many, females are pretty tall. Okay? All right? So here, the stories really tell us that by theory, maybe gender, the direction, the expected sign of the height may not be that clear. Does that make sense to you? Does not make that clear. Okay? All right. I think we will say all this important implication for all this result later on in chapter 4 and chapter 5. Okay? All right.
For the moreover, for the R square does not change after we adjust gender to the equation, and we found the adjust R square decrease from 0.205 to 0.216. This means that the gender dummy variable cannot predict the weight. Right.
Okay, can you explain the coefficient with these two models? Either one of them.
Is the one.
Why? How about using the pounds and inches? Okay, explain the coefficient.
For the pound, if holding high as constant, if there is one holding gender as constant, if there is one FD is 1 pound increase, then there will be 6.62 inches by increase.
Well, no. Say it again. Holding males as holding gender as a constant, then
holding gender as constant, if there is 1 inches increase, then there will be 6.625 pounds by increase.
I don't say it clearly, okay? Say it again.
Okay. Holding high as constant, if there is if there is one
No, height. The coefficient of height. Explain the coefficient of height.
Holding high, like teacher, or holding teacher.
Explain the coefficient of height.
For the height of the kilogram and centimeter, for the height in kilogram per centimeter units, the height
No.
is
I don't understand what you're saying right now. explain the coefficient of height. Say it.
In PowerPoint in slide, teacher.
Huh?
In PowerPoint or in kilograms per centimeter.
I don't understand you. Holding gender as a constant. Then
the height is 1 inches increase. Then the
height increase
height increase
by
by
1 inch.
1 inch.
1 inch.
1 inch.
1 inch. Then
there will be 6.625.
Then weight increase by
Then weight increase by
6.62.
6.62.
Okay, try to learn how to express by yourself. Okay, if you don't know how to make a sentence, read the textbook. Okay, the textbook show you how, they have the expressions. So try to learn it. Okay, try to learn how to express the correct way. I think this is important. Okay, so would you like to say it again? Coefficient for height.
Teacher again, please.
Holding gender as a constant.
Holding gender
As a constant.
as constant.
Yeah.
Holding gender as constant.
If height
If height
increases
increase
1 inches,
1 inches,
then
then
the weight
the weight
will increase by
the weight will increase by 6.62
pounds.
pounds.
Okay, is that clear? Yeah, okay. Then anything else? So what is this?
We enter the coefficient and the mutual.
Okay, just the equations. Okay, anything else? All right, thank you very much. Okay, with all the projects, okay, I know that we have different data set. Therefore, when you run the regressions with the same regression, same y variable and x variables, and different data set, the result is totally different. But do you find out that some of the project, since we want to compare with the equation from textbook, so equation 2.6 is the measurement units for y and x is in pounds and inches, right? So if you compare your result with the equation 2.6 from the textbook, some of the project, I know some of you get the pretty close coefficient, something like 6 or around 6 for your from your data, but some of them, is really different. Okay, so you will know that all these estimates. What I mean is, I'm using the models with gender, okay? and we do the expectation. This is all the result from output. And we explain the meaning of this one. Okay? And all these coefficients is using what we say OLS methods. So this is what we say the estimator so far. All the regression was running by using OLS. Okay, this is very basic regression technique. Okay, and when we run the OLS, and you will get the beta 1 hat is by some formulas. Okay, you will get beta 2 is also by the formulas we had in our textbook. Okay, those OLS, those formulas is what we say estimator. The OLS is the estimator, and using this OLS technique, then we come up with these formulas. So if we have all these numbers plugged in, then we will have the number just exactly as what the computer output showed us. Okay, so since you have different Y and X, all of you, we have A projects, A data set. All the data sets with different Y and X, but same measurement units. Therefore, we end up with those beta 0, beta 1, and beta 2 are different. Therefore, with your project, we have A project. The A project, we have 8 beta 1. We have 8 different beta 2 hat. Okay? All right? And this is what we wanted to say, that the OLS, okay, have some properties, okay? And with these properties, we need to have some assumptions. This is why we say in chapter 4 that what we call this one is a classical model. Okay, classical model with 6 or 7 assumptions. Then we have some properties to say something about this beta 1 hat and beta 2 hat. Okay, so we need to learn those 6 or 7 assumptions. And what are they? I think we mentioned it last week, right? Which is in our textbook on page 111, I think. Okay, so I hope all of you can make a note from this page, okay? Although you are not really quite understand all of them, but you need to understand that with all these 7, or we say 6 assumptions, then we are using in statistics is called let's see, what we call the Gauss-Markov theorem. Okay, which is in 4.3, Gauss-Markov theorem. Okay, let me show some of the PowerPoint. I have it from. Did I have it? Where is it? Okay, here. So I like to review all these 7 assumptions. Okay, remember we explained this one last week. The regression model is linear, correctly specified, and has additive arrow terms. What do we mean by linear? Means linear in the parameters, or linear in the coefficient. Okay, linear in the coefficient instead of linear in the variable. Although, if you have linear in the variable, that's fine too. Okay, but the essential part is linear in the coefficient. So it means this one, linear. So linear in the coefficient means the power of all these coefficients raised to only 1, none else. Okay, all right. The second one is the arrow term has a 0 population mean. I already explained it. Some positive difference, the other one is negative difference, and the best model should cancel out this positive and negative. Okay, the third one is explanatory variable. X variable is uncorrelated with the error term. In other words, all the X variable is collected or choose by the literature review, okay, by literature. So whatever we want to study, what is Y, then you choose the related or important X variables included in the model. Then all these X variables is to explain the variation of the Y variables. Therefore, those error terms is just random error. Okay? If you have something for explanatory variables related to error terms, means what? If you have explanatory variables in the error term, means what? Means there's some information, in the error terms which did not extract from the error term, that included it in the X variable. Okay, in that case, all the estimation of the beta will be incorrect. Okay, and we also say that the fourth one is observations of error terms are uncorrelated with each other, and this is totally related to time series data. Okay, so we have two different types of data: time series data and also cross-sectional data. And this assumption is really related to time series data. So in the future, we'll work with time series data. These assumptions, should be play the important role. But for cross-sectional data, these assumptions plays the important role. Okay, so this one is for time series data, and this one is for cross-sectional data. And the cross-sectional data tell us that the error term has a constant variance. It means that the X values won't affect the large variation of the Y variables. Okay, if X variable will affect the Y variables, okay, there's a good chart. I think we can we see from here? This is the chart. Did you see this chart? 4.2 in our textbook. Okay, this means that the Y variable is here, and this one is one of the X variables. If the charts, look at this chart. How do you see those dots is the sample? Okay, how do you see? Did you see when you see the graph like this one? Did you see some information from this graph? Look at all this graph. It's like trumpet. Did you see the trumpet? The pattern of this graph. Did you see just like trumpet? Means that when the X variable is small, those dots just close together. But when the X variables become larger, then there's big difference. So this case means that the X variable and the X variable will means the fourth assumptions. What do I mean? This one. The error terms do not have constant variance, because the X variables, the Y variables. Look at this one. When X variable increases, the Y values increase. Okay, then what do we mean by the constant variance? If we see the diagram, something like this one, If this assumption met, x, what do you mean by this one? No, I should put this one. This is arrow terms, okay, instead of y. This is arrow terms. Okay, the arrow terms won't be increased by the x variables. This means in what level of x variables, the variance is the same. Okay, we will get to this one later on, okay? All right. Then what else? What's the assumptions? Okay, number 6. No explanatory variable is perfect linear function of any other explanatory variables. I think now we can say something about this one. Okay? What do we mean by perfect linear function of any other explanation variables? In the math, if I have this two variables, one is called x1, the other one is called x2. Okay? When we say perfect linear function of any other explanatory variables, means if x2 equal to a plus b x1 or some other functional form in math, okay? If we can say x2 equal to a plus b x1, this a and b, let me just show the numbers, okay? 3.2 plus 2x1. What does that mean? What does that mean? If you know x1, then you know x2, right? So actually, does x2 provide extra information for y in addition to x1? My question is, if x2 and x1 has the relationship like this one, then does x2 provide extra information to explain the variation of y instead of x1? No, since x2 can be expressed as 3 plus 2x1. So as long as x1 is given, means as long as I know the x1, then I will know the x2. Okay? Therefore, these equations, since, from this expression, x1 and x2 are different. In fact, it is the same. Why? Because I can replace x2 with this relationship, right? So I'll say here, So it turned out to be beta 0 plus 3 beta 2 plus beta 1 plus 2 beta 2 x1. So in other words, this one, in fact, is this one. So looks like x1 and x2 with x1 and x2 are multiple regression, two variables. But in fact, it is just one variable, which is x1. So x2 doesn't provide extra information to explain the variation of y in addition to x1. Understand what I'm saying here? All the variables in the models, individual x variable should play its own role to explain the relationship of the y variables. That's why we need to, choose those variables to explain the variation of the y. But if these variables, in fact, has perfect relationship with the other explanatory variable, for example, x2 can be explained to this relationship, then this x2 doesn't provide extra information. And in fact, these two are the same variables. Okay, so this is the definition or the assumptions from number 6. No explanatory variable is perfect linear. Perfect linear. When we say perfect linear, it's exactly relationship. If I put it here, something like arrow terms. If I put it here, then these two are different. If I say x2 is something like this one plus this, then x2 and x1 are not perfect linear relationship, but highly correlated. Highly correlated, right? So this is when we say perfect and without perfect, the meaning of the perfect and without perfect. So actually, multicollinearity is another problem. And when we say the multicollinearities, it means something, which is not perfect. And in reality, it is in this way too. It's really hard to find any x1 and x2. It's totally different when we do the research. Okay, exactly, no relationship. No, it's pretty hard, especially in business world, and also in some other, science, in like education area. Okay, so this is number 6. And number 7, when we do this normal distribution is for hypothesis testing. Okay, so with this 7 assumptions, okay, then end up with, we need to know the sampling distribution of the beta hat. Means that, like we have the A projects, we end up with a different beta hat for our data set. Okay, since we use different data set, okay, therefore we have different beta 1 hat and beta 2 hat. All right, so the sampling distribution tell us what? Okay, if we have the assumption of normal distribution, okay, and in statistics it's already proved, okay, and there's some properties of the sampling distribution of the beta hat, okay, and what do we mean by the sampling distribution? The probability distribution of beta values across different samples is called the sampling distribution of the beta hat. It means that if we can collect all the possible data set, then we will end up with infinitive beta hat, right? And if all those beta hat, we draw the diagram, it end up with a probability distribution. So for, we have our example, some of them, you have this, the coefficient of the height and the weight is 6 point something. Okay, so if we are using pounds and inches as a measurement units, if the parameters, I mean the real relationship between the height and the pound, the height and the weight is something like 6. I just, for example, But when you collect all the data, okay, some of them will end up with pretty close to the 6. Some of them is really far away from 6. Okay, and all these numbers, if I can collect as many as possible, then if I draw the diagram and it turned out to be a probability distribution, and this is what we call sampling distribution of the beta hat. And mathematically, with the assumption of normal distribution, then it can show that, like this one. This is the example that they're using, they're using also the height and weight, like our examples, and they are collecting 100 samples. Okay, then they draw the diagrams. Okay, so in theory, when we can collect the sample as many as possible, it turns out to be the distribution of the beta hat. Okay, and there are some properties. Look at this one. To be good, an estimation technique should be unbiased. So there are some terms maybe you have to understand it. This is called unbiased. What do we mean by unbiased? It means that if we don't know, but if the real beta, no hat, if the real beta means the parameters is 6, but beta hat is different from 6. It can be, some of them can be close to it, and some of them be far behind it. Okay? No matter what, the good estimation, when we say unbiased, means the expected value of all the, let me show this one. The expected value of all the beta hat is equal to beta. What do we mean by this one? This means that all the different beta hat from different samples and the expected value. When we say expected value means the average of them. If it is the same as the beta, then we can say something using the probability distribution to describe the relationship between X and Y. Okay? All right? This is the basic statistic, theory, concept about hypothesis testing. Okay, that's why we are saying we need to say the sampling distribution. So when we say the sampling distribution of the beta hat, let's see. What's the difference between these 3 distributions? Okay, we call this one as A, and this one as B, and this one as C. Okay, and if we know the true beta here's the true beta. Okay, and what's the difference between A and B? Look at distribution. I think it's easier to see the graph instead of see the math. Okay, what's the difference between A and B? Look at both of them, the highest parts. Okay, the highest parts is in beta. The location here. Here is the location of beta. So for A and B, the expected value is also equal to beta. So it meets the requirements of this one. Therefore, A and B are all unbiased. Look at C. The location of the distribution of C is at the right-hand side of beta. Okay? So this means it is far beyond the beta. So it may have the distribution which is not on the right-hand side. Maybe it's on the left-hand side. Either right-hand side or left-hand side is always say the true, this distribution's beta is different from the true beta. Okay? Okay, this is the first properties. Unbiased means the expected value of the beta should be equal to beta. And OL as estimator meet these requirements. Okay, therefore we're using OLS. Okay, and what about the second, okay, look at this one. Okay, this one, what's the difference between these three? They are all in the center is equal to 1. Did you see that? And the difference between these three is the lowest one. I mean, the lowest one is with the sample size equal to 6 only. And the middle one is the sample size with 60. The highest one is with sample size 600. Okay? So this means that if we do have sample from the same population, but if your sample size only 6, the distribution is fatter. When we say distribution fatter, what do we mean by that? It means that the variation of the value of individual data set, individual, is quite different. It's quite different. But if you have the sample size which is 60, is larger, right? And it's become in the middle one, which is getting, the distribution of this one is getting smaller. So means the expected value beta hat, although they are different, but the variation among them is getting smaller. Okay? And if you have the 600 sample size, it's getting even smaller. It means that although you have different beta hat, but the difference among them is getting even smaller. So which one do you like? Yes? Huh? 600? Yeah, of course, we need the one with the variance is smaller. Okay? This is the diagram showed us that in real world, if we do this research, we need to collect as many as possible that we can collect the data as big as enough. The more data you collect, the more precise of the beta you will get. Understand what I'm saying here? Okay, so this is all about in chapter 4. Okay, I like all of you, especially you understand. You read the chapters. If you don't quite understand all those statistical concepts, never mind. See the diagram. Okay, if you can catch the information from the diagram, I think you catch the essence of chapter 4. I know that there's many abstract concepts inside it, okay? But we're not focused on this abstract concept, okay? So the OLS, the method we using, they do have the property of expected value, and they do provide the beta with the smallest variance. Okay, this is what we say in the Markov theorem in 4.3, in section 4.3. Okay, and I'll finish the last parts. Okay, be careful all these notations. Okay, in the future we will use all this notation in our textbook. Okay, and whatever said here, this is called population parameter. Okay, so when you see the notations like this one, it is talking about the populations. And when you see the notation like this one, it's called estimate. Okay, estimate is by population, by samples, and the parameters usually is from population. So you should, pretty focus on the notation. Okay, in order to know which is population, which is from sample. Okay, I think that's for today and also for chapter 4. Okay, read the chapter 4 by yourself. Okay, but don't worry too much about the chapter 4 when you read it. Okay, then next week I'm going to start it for chapter 5. Okay, chapter 5 is hypothesis testing. I think I'm going to spend about 1 month to say the hypothesis testing is real important. Okay, all right, this is the basic and also the foundation of regression analysis. Okay, that's for today.